In this next series of videos, we're going to be taking a look at the addition of nucleophiles to alkene systems and to aromatic systems. So in the reactions that we've learned so far this semester, in all of them, in fact, we're using pi electrons as nucleophilic electrons. We learned about electrophilic addition to alkenes, and we know in this case we're taking some electrophile and adding that alkene to the electrophile to make a new, in this case, carbon electrophile bond. And this results in the immediate formation of a carbocation. Enolate anions are really just activated alkenes, right? Because they have an oxygen in conjugation with the pi system. And so they're going to react in much the same way, where again we're making a carbon electrophile bond, but in this case the electrons are being pushed out by the oxygen. Most recently we learned about electrophilic aromatic substitution, and we know that if we mix a correct electrophile with an aromatic system, we can use that aromatic system as a nucleophile and again make a new carbon electrophile bond. In substitution, this is going to be two steps, remember. So the first step is the electrophilic addition. In this new section, rather than adding electrophiles to alkenes, we're going to be adding nucleophiles to alkenes. And the two types of reactions that we're going to focus on are conjugate addition, or addition to activated alkenes, and nucleophilic aromatic substitution. So in conjugate addition, what we're doing is we're taking a nucleophile and we're adding that nucleophile to a pi system, breaking that pi system, and then shifting those pi electrons to an adjacent carbon to form an anion. Now this is a very simplistic view, and we're going to look in a little bit what these systems really look like, because this reaction is not really possible, where we can take a nucleophile and add it to propene and get some reaction or some bond formation. Right? And then when this reaction is over, much of the time it's just quenched using a protoquench, and you've accomplished your nucleophilic addition to an alkene. Right? Nucleophilic aromatic substitution. Similar in effect to electrophilic aromatic substitution. The only difference is, rather than adding an electrophile to an aromatic system, we're adding a nucleophile to an aromatic system. So again, this nucleophile adds to the aromatic pi system. We're shifting electrons to one of the positions around the ring. So the first step is addition, and then the second step is going to be an elimination, and this gives us a net substitution. Right, so as you can see in electrophilic aromatic substitution or electrophilic addition, we're using the pi electrons to add to an electrophile. In conjugate addition and nucleophilic aromatic substitution, we're using a nucleophile and adding that nucleophile to the pi system to create an anionic intermediate. Now, if we think back to electrophilic addition reactions, right, we know that these reactions will work best whenever we can form a stable intermediate, right? So anything that we can structurally change about this alkene to give us a stable cationic intermediate is going to help with that reaction. So for example, in just standard alkene addition, right, if we start with a starting material that gives us a tertiary carbocation or a more stabilized carbocation, then we know this is going to be a more stable or a more likely reaction to occur, right? We can think of enolates as kind of like activated alkenes, or we can think of them as very stable cationic intermediates, right? So you can imagine if we didn't push the electrons from oxygen down in this product or in this intermediate, we would have a positive charge here that's obviously stabilized by the oxygen, right? And likewise, if we put an electron donating group onto that benzene ring, right? That's going to help stabilize the uranium intermediate, lower the rate of the reaction, and make it more possible. Well, with nucleophilic addition to alkenes, we are also focusing on the stability of that intermediate as a gauge for how easily these reactions can proceed. Right, so if you look at this reaction, this is a two-step reaction, adding a nucleophile to the pi system, forming an anionic intermediate, and then protonating or quenching that anionic intermediate with a proton, right? So this is the addition step. Anything that we can do to stabilize this intermediate is going to speed up that reaction and lower the energy barrier of that first step. So you can imagine if we put an electron withdrawing group on here, right, now we have an anion next to an electron withdrawing group. Well, this electron withdrawing group is going to stabilize the anion. Likewise, when we do nucleophilic aromatic substitution, again, we're creating an anionic intermediate. And so if we, on this ring, put an electron withdrawing group, we're not going to really focus on where on the ring it's going to be right now, but some group that can withdraw electron density, help stabilize that anion, that's going to be able to speed up this reaction and make it much more favorable. Right? So again, if we think about these three reactions or these three processes, electrophilic addition, right? In this case, we are going to have nucleophilic pi systems. Whereas in these two new reactions, conjugate addition and nucleophilic aromatic substitution, these are going to be electrophilic pi systems. So we're going to be looking at both of these reactions in this chapter, but we're going to start off by looking at the conjugate addition and then move into nucleophilic aromatic substitution. So conjugate addition goes by a couple of different names. So a lot of times you'll hear conjugate addition referred to as Michael addition or 1,4 addition. All right. And again, what we're doing in this reaction is we're taking some nucleophile, right, adding that nucleophile to an activated alkene. And when I say activated alkene, that means that we have an alkene in conjugation with an electron withdrawing group, forming an anionic intermediate, which is then quenched. In this case, we'll say by a protic quench. There are different ways to quench these reactions, but we're going to right now, just for simplicity, look at just adding a proton to that anion. Now, before we get too far, I want to look a little more closely at what this electron withdrawing group is. All right, and so the compounds that we're going to focus mostly on are going to be alpha-beta unsaturated carbonyl compounds. Right, you can imagine if we add a nucleophile to this beta position, and this is why it's called an alpha-beta unsaturated carbonyl. If we add a nucleophile to this beta position, that's going to allow us to push that electron density all the way up to the carbonyl oxygen. All right, similar to an alpha-beta unsaturated carbonyl are going to be alpha-beta unsaturated nitriles. Right? And we also have alpha-beta unsaturated nitrosystems. Right? And hopefully what you can see in these starting materials, in these activated alkenes, is that each of them features an alkene that's in conjugation with a carbonyl, a nitrile, or a nitro group, right? So there's a pi system, an electron withdrawing pi system that's in conjugation with the alkene that is serving as the electrophile in each of these reactions, right? If we think about the reactivity of these, and we're going to really focus for most of the reactions on the alpha-beta unsaturated carbonyl rather than the alpha-beta unsaturated nitrile or the nitroalkene. It helps to understand the reactivity of these molecules by thinking about the resonance structures that we can draw from an alpha-beta unsaturated carbonyl. All right, so this R group is just going to stand in. This carbonyl can be an ester, it could be an amide, it could be a ketone, it could be an aldehyde, right? That R group, we're just saying that it's some carbonyl. Well, we understand how carbonyls can be electrophilic by drawing a resonance structure, realizing that the oxygen is more electronegative, right? And when that pi system breaks, those pi electrons are going to go towards the more electronegative atom, right? And so this resonance structure illustrates some of the reactivity of a carbonyl, right? Showing that the carbon has a positive charge, formal positive charge in this resonance structure. Oxygen has a formal negative charge. And we know that resonance structures are an overall average of all of the resonance. Well, hopefully we can see how this beta position is also going to be electrophilic, because if we just shift those electrons over to fill that positive charge, well, that puts the positive charge on that beta carbon. And so what this means is that not only is the beta carbon electrophilic, or the carbonyl carbon electrophilic, but the beta carbon is also electrophilic. Now, when we add a nucleophile to an alpha-beta unsaturated carbonyl, say we want to do a Grignard reaction. So we'll add phenyl Grignard and then work up the reaction with water. Well, we're going to see a couple of different products, right? We would expect to see a product where the Grignard adds to the carbonyl carbon. To create an alcohol. Right? But we would also expect a product where the Grignard reaction or the Grignard reagent adds to the beta carbon. Right? And so these are the two products that we would get, right? One where the Grignard reagent adds just to the carbonyl carbon, and then one where the Grignard reagent adds to the beta carbon first, followed by the carbonyl carbon second. So let's take a look at that reaction a little more closely. So we know that addition to the carbonyl by a Grignard reagent is very possible, right? And this would give us a direct addition to the carbonyl and give us this alcohol. Upon quenching, or this alkoxide, upon quenching would afford the alcohol. However, if we add to the other carbon, you can see the electrons shift all the way up to oxygen. We're forming an enolate intermediate. And then this will be quenched by a proton. You can see our carbonyl is still intact, so if we do another reaction with phenylmagnesium bromide, right, that's how we would add our second phenyl group. So when we're talking about addition to alpha-beta unsaturated carbonyls, right, we can use numbers to describe where that nucleophile is being added. And so in this case, this would be considered 1,2 addition, where the nucleophile is being added directly to the carbonyl, because you can see the relationship between the oxygen that ends up getting the electrons and the carbonyl carbon where the nucleophile is being added. In the case of conjugate addition, we would refer to this as 1,4 addition. Because the relationship between the oxygen that gets electrons and the carbonyl carbon that's accepting the nucleophile is a 1,4 relationship. Now there are some nucleophiles that preferentially add in a 1,4 in a 1,4 aspect, and there are some nucleophiles that preferentially do 1,2 addition. And in a future video we're going to go over the difference in those nucleophiles and also the difference in electrophilicity. But before we end this video, I do want to sketch out what the lowest unoccupied molecular orbital looks like for these systems. So remember, if we're using this carbonyl system as an electrophile, that means that the lowest unoccupied molecular orbital is coming from this carbonyl system. And when we're adding a nucleophile to the carbonyl system, we're not adding to the alkene, we're not adding to the carbonyl, but we're adding to the overall pi system. So what does that look like? Well, we have our 4 carbons, and each carbon is going to have, our 3 carbons and our oxygen. Right? And our pi system is going to be on each of those 4 atoms. Now if you think back to the first semester when we looked at conjugation in organic molecules, we went over the molecular orbitals of 1,3-butadiene. And these molecular orbitals are not going to be very much different from 1,3-butadiene. The size or the coefficient of each orbital might be different, but the overall phase interaction is going to be the same. So the LUMO of an alpha-beta unsaturated carbonyl is going to have an out-of-phase interaction between the alkene and an out-of-phase interaction between the pi system of the carbonyl, but an in-phase interaction in the middle. And so this is what the LUMO looks like of this pi system. And when we add our nucleophile, so this would be referred to as the pi star LUMO. When we add our nucleophile, that nucleophile is going to be added to that carbonyl carbon. Now when we talk about the pi star, right, again, the pi star is not this carbon-carbon pi star. It's not the carbon-oxygen or the carbonyl pi star, right, but it's the pi star of the overall pi system. And that's where the nucleophile is being added. So it's important to understand this a little bit to understand the different nucleophiles that can be added and their selectivity towards addition. And in future videos we're going to take a look at how different nucleophiles and the properties, the different properties that those nucleophiles have, are going to determine where they're added to an alpha-beta unsaturated carbonyl.